Thank you a lot for giving me the opportunity to present here. I'm Sebastian Nehrdich, and I'm today going to present on the Mitra system that we are developing at the University of California, Berkeley, together with David Allport, Jivnesh, Sandhan, Sujit Jaiswal, and Kurt Keutzer. And our system is basically a machine translation and large language model powered grammatical explanation system for classical Sanskrit.
Dr. Sebastian, can you can you keep your presentation please on the presentation mode or full screen?
Oh yeah, sure. You mean like this?
Yes. Thank you.
Okay.
Please continue.
Okay, great. Yeah. So I will first give a brief introduction of the Mitra project and team. Then I will give an overview of the architecture, of the grammatical preprocessing step that we are proposing, the machine translation, and I will also give one example of the system in action, and I will give an outlook of further work that we are planning to do. So the team, basically, it's a bit too much detail to go into all the names now, but just as an overview, there's Kurt, executive director, then I am the technical director, David Allport is working on Sanskrit data collection, and then we have Jivnesh and Sujit, who work together with a number of graduate students to collect data. And we also have a number of students and interns at UC Berkeley who help us and who work together with us to create the necessary data set for this type of work. So the architecture of the machine translation explanation system that we propose is we take Sanskrit input sentences and we process them in multiple steps. So the first step is grammatical preprocessing, where we do segmentation, lemmatization, and morphosyntactic tagging. Then the next step is we use an encoder-decoder language model to generate a draft translation. Then we use k-nearest neighbor search. So that's basically a search system where we can query an index and get the 5 or 10 or 15 closest, most similar sentences to our input sentence. And in that way, we can gather few short examples for the language model. So we can say, here are 5 Sanskrit sentences translated into English from our reference database. You can use them as examples to learn from them, to get some clues on how to translate. So that is a technique that can improve the quality of the translation here. And then with all these different information that we have gathered, we can prompt a large language model such as ChatGPT, Claude, Gemini, and so on, in order to generate a precise translation together with a grammatical explanation if that is desired. So this is an overview diagram to show how the workflow of the system works. So here we have the Sanskrit input sentence, that's our starting point. And then we have the step of Sandy split, lemmatization, morphosyntax tagging. We also have the step of machine translation, which can actually be done in parallel. And then we also query the KNN index in order to get the number of examples from the reference corpus that we want to include at that point. And once we have gathered all this data, we can combine it into one prompt that we feed into a large language model. And then we ask the large language model to produce us, based on all of this information, a translation or a grammatical explanation of our Sanskrit sentence. So what is the motivation behind creating this machine translation and explanation system? So first of all, translation models such as Google Translate or transformer models trained from scratch, they are limited in their capabilities. So they cannot explain how a translation was derived, and we as users of these systems are basically sitting in front of a black box. So we can paste the sentence into Google Translate and we get a translation, but we cannot tell, if it's right. We don't know how was this translation generated? How did the machine come to that conclusion? So large language models, on the other hand, they do have this ability, and they show powerful performance on general natural language understanding tasks, but they lack the domain-specific knowledge for Sanskrit, and they are prone to show hallucinations, imprecise renderings of grammar, and so on. And I think this is familiar to many people in the audience here who have tried to use ChatGPT to translate Sanskrit. It's not always on point. And if you ask ChatGPT to explain the translation, then it can get more fuzzy and there are more mistakes, hallucinations, and sometimes it's just downright wrong. And that's why we want to build this tool chain, in order to avoid the model to get off the rails and produce wrong output. Then currently the grammatical preprocessing tools are efficient and sufficiently precise, but they do not output machine translations, and they also don't present the results in an easy to understand manner. Few short examples actually can further increase the quality of translation when high quality data is available. So this is a so-called nearest neighbor machine translation paradigm, where a machine translation model is combined with a reference database in order to generate higher quality machine translations. Now, when we combine all of these different aspects, grammatical processing, pre-generated machine translation, and few short examples, we can query a large language model with strong reasoning capabilities in order to generate high quality Sanskrit translations, together with easy to understand explanation of the grammatical structure of the Sanskrit. And this flow can be described as a sort of linguistically informed chain of thought prompting for machine translation. So I just want to give an example of the grammatical information that is stored in the digital corpus of Sanskrit from Oliver Helwig, which we are using as the basis of the data for the generation of the grammatical explanation system. So this is how the data is stored in the database, and we can already see that this is, from a linguistic point of view, of course, very important, very valuable data of high quality, but at the same time, it's not immediately user-friendly to use. So when a tool outputs data in this format, it needs some post-processing, either in the form of a web interface or some language model that actually digests this and gives it in a nice, presentable way. And in order to generate these grammatical explanations, we are proposing the training of an encoder-decoder model to perform Sandhi segmentation, lemmatization, and morphosyntactic tagging jointly. So this is all done in one model. We use the MT5 model of Google as a base model for this. The data we are actually taking from Oliver Helwig's digital corpus of Sanskrit. And then we also perform simple post-processing in order to make the output more prompt-friendly, because the prompt systems are tuned to digest natural language. So this conlu format needs to be converted into some kind of natural language so that the model can actually work with that. Coming to the draft machine translation steps, so we have an ongoing effort of data collection here at UC Berkeley since the summer of 2023, and currently we have more than 718,000 aligned BTEX pairs of Sanskrit and English data. The publication of the data set and the machine translation model rates are planned for 2024, and we also plan to release the machine translation and grammatical explanation tool for a limited audience, targeted audience in the summer of 2024. There are, of course, some problems that we still need to sort out, like, for example, the running cost of GPT in the inference. And for that reason, we just cannot make this available to a large audience right now. We need to sort out these details first. Coming to the machine translation data collection. So currently, I guess I cannot go through all of these numbers now in detail, but just to give a large picture of how our data is constituted, which different elements we have. You can see coverage for epic and Purana text is pretty good. For scriptures, it's not as good. For treatises, we are doing not so bad, but it could be better. Poetry, I think it's still a lot of room of improvement. Vedic material, of course, as well. The coverage is not very far at the moment. So, but all in all, we have managed to gather about 22% of the available data, and our reference corpus here is the Gretel corpus of University of Göttingen. So of that corpus, we have been able to cover about 22%, and we hope to be able to improve this number in the coming months and years. Now, to give one example of how this system might look like in action. So this is, I just took this screenshot this morning in order to include it in this presentation. So this is really as fresh and live as possible. And I have taken the first Karika of the Nala and Damayanti story, which is used frequently in Sanskrit textbooks in order to teach Sanskrit. And I hope the English translation that we have here, there was a king named Nala, the valiant son of Vidasena, endowed with desirable virtues, handsome and skilled in horsemanship. I hope this is acceptable. Maybe some Sanskrit experts find some point of criticism, but let's hope it's good enough. And then we get the grammatical explanation. So asid is derived from the root as, it means to be, and here it is used in the indicative mood, singular number, past tense, translating to there was. Raja is the nominative singular form of Raja, meaning king, indicating the subject of the sentence here, and so on and so on. I can't explain the whole example here, but as you can see, there's a lot more linguistic information and precision in this system than any generative AI system like GPT or Gemini or whatever would be able to provide at the moment. So,
Dr. Sebastian, can you zoom in?
That the prompt system is working. Yeah, sorry?
Can you zoom in? We can't see that translation clearly.
Yeah.
Oh,
I don't know
presentation.
How to zoom in the
okay.
Mode, so,
okay.
Yeah, I'm sorry, but I can, yeah.
Okay, it's okay. Continue,
that,
please.
Yeah. Okay, regarding further work, so the outlook is, of course, collecting more parallel sentence data is very, very important, because the better the reference data is, the better the training data for the draft translation system is, the more reliable this whole pipeline is going to work. So we are putting a lot of effort into getting more data. And we also want to reach out and, if anybody in the audience feels this is an interesting project, I want to also be part of that. I want to contribute. I want to see how we can improve the quality. Then feel free to contact us. We are certainly looking for partners for collaboration for institutions. This is something like we really want to develop in an open fashion together with other people. So if you're interested in this, we are more than welcome to collaborate. Now, the data cleaning and improvement of alignment quality is an ongoing issue, and we are currently scrutinizing and trying to improve as much as possible on that end. So that's also a challenge. Then what we also plan is the integration of a corpus-wide semantic search tool that can provide relevant passages with similar content. So we can, for example, in the Geräte corpus or in other collections, we can search, and if there's a similar Karika, we can fetch that from the database and then also give the user some references. This Karika you want to translate is also quoted here and there, so that can give additional meaningful information to the users. And lastly, we also want to explore the fine-tuning of open source large language models to reduce the reliance on commercial providers. So right now we develop the system by using the API of OpenAI, but of course, sooner or later, having our own independent model is very desirable, and we really want to work towards that end as well. Yeah. I think that's all from our side, and thank you so much first.
Thank you so much, Dr. Sebastian. And questions, yes.
Thank you, Sebastian. It was a very wonderful presentation. And what I like the most is you are not just producing the translation, but you are also giving the morphological information and segmentation and other things which are very much relevant. But here I have a question. When I saw your workflow, I noticed that translations are coming from different sources and the morphological information is coming from a different source. So, do you don't you think there will be cases where the translation is different and the morphological information that you are displaying is totally irrelevant?
I think it's a very good point that you make, and it's one of the great challenges that we have here. So just to show the workflow, it's of course very much possible and maybe even desired to change the order and to, for example, do the Sandhi splitting, lemmatization, and morphosyntax tagging before we feed the data into the translation model. So that is one way to make sure that the translation model is based on the same grammatical annotation that we have provided at this point. So that's one thing. the problem is in practice. It sounds nicer on paper than it is in practice, because since Sanskrit is such a morphologically rich language and we can encode so much, it's actually possible that we run into the problem that you just described, that the grammatical annotation tool is producing something that conflicts with the recorded translation data of our data set. So we have the collected sentence pairs, and they might have a different decision than the parser, the grammatical annotator is doing in the step before. So our experiments to train a translation system on top of the grammatical annotation systems have not always yielded that great results. So this is an ongoing process. So we are trying to explore what is the best way here, and it's still not, I think we are not there yet that we can say we have solved this. And it's really challenging, because those conflicts in grammatical annotation and translation from the data side of view are very difficult to solve, because that would require basically retranslating the Sanskrit based on our grammatical parsing, or it would require to re-annotate the Sanskrit based on our English translations. And both is probably something that is well beyond what we can do as a team. So yeah, this is a challenging situation, absolutely. And especially on more complex verses, this can really become a problem. So yeah, there are certainly shortcomings here that will undoubtedly emerge later on.
Yeah, so here one suggestion is to plug in the dictionaries. Since you have the root words and you have the dictionary, and then use these dictionaries to map or correlate them with the translations, and then you make sure that there is convergence kind of thing. Thank you.
Yes, we have also worked with, so just to quickly respond to the dictionary, so we have tried that, and the problem at the moment is that it's actually giving too much information to the prompt of the large language model, and it's actually getting confused, because we have the dictionaries like Moni-Williams have so much for certain words. They have such an overgeneration of possible meanings, which makes sense. Of course, we know Sanskrit is extremely productive and the meanings can be really deep and manifold. So actually limiting the dictionary to what is relevant to the actual sentence is another challenge. We have some ideas on how we can tackle that, and I fully agree that this information should be included. Yeah.
That you can do by looking at the translation. From the translation, you know what sense is there, and then pick up the corresponding sense, and this will also give you another resource where you have sense tagged it. But you need to look at the translation as well as the dictionaries. Okay.
Yeah, I fully agree with that idea to use the machine translation, because then basically we can just embed the dictionary entries and the machine translation in vectors, and then sort the dictionary entries according to their similarity to the translation and rank them in that way, and then limit to just the first 4 or 5 entries. So in that way, this overgeneration problem is solved. Yeah, I think that makes a lot of sense. Yeah.
Okay. Yeah. Let's thank Dr. Sebastian one more time for his presentation. Thank you, Dr. Sebastian.